In this video, I want to have a look at definite integrals. So far when we've been integrating, we've been looking at finding areas underneath curves, but they've always been above the x-axis. So what we want to have a look at now is what happens when that function dips below the x-axis. So for example, if we wanted to find integrate this function between the values of a and b over here. So that means we want to find the whole area between the x-axis and the curve. So it's going to be sort of three separate areas. So let's call them A, B, and C. Then what actually happens is if we're finding the integral from A to B, so this function is f of x dx, these values that are underneath that x-axis are actually going to contribute negative values to our integral. So we'd actually have a plus c, so these two values that are above the x-axis, minus whatever b is. So to have a look at an example of how that works, I've got two functions drawn here. My first one is the function 3x squared, and my second one, we've got fx equals minus 3x squared. So it's the same curve, just this second one's been flipped upside down. Now in this first question, we want to find the integral from 0 to 2 underneath that curve. So 2's here, so we can shade that region in so we can see what it looks like. And it'd be this section under here. Now in our second one, we still want to find it between the x values of 0 and 2. So what you can see already is that they're actually the same size, those areas. But let's have a look at what happens when we integrate them. So finding the primitive of 3x squared would give us x cubed, and we want it between 2 and 0. So we'd have 2 cubed minus 0 cubed, which would give us 8. In this second one, the primitive of that would give us minus x cubed, and we still want between 2 and 0. So now we have minus 2 cubed minus 0 cubed, and we would end up with minus 8 because that negative isn't in with the x with the cubed, so it's minus 2 cubed. So they are the same size, but because this area is below the x-axis, it's giving us a negative value instead. We'll look at an example that involves areas above and below the axis at the same time. So in this one, we've got the function x minus 2, and we're asked to find the integral between minus 2 and 4. So that's this section here. So we've got this bit underneath the axis and this bit above. So when we find the primitive of that, we would have x squared over 2 minus 2x, and we want that between 4 and minus 2. So substituting that in, we'd have 4 squared over 2, that's a 2, not a 4, minus 2 times 4, minus, then we'd have minus 2 squared over 2, minus 2 times minus 2. So it's going to give us 4 squared is 16, divided by 2 is 8, minus 8. Then we can have minus 2 squared is 4, and 4 over 2 is 2, and minus 2 times minus 2 is plus 4. So that's going to give us 0 minus 6, which is just minus 6. So it's like this area minus this whole area will give us minus 6. Another thing that's important to know is that if our functions have odd or even symmetry, we can use those to help make our calculations of our integrals a little bit easier. So for example, if we look back at this parabola, we know that that has even symmetry because it has that reflective symmetry across the y-axis. Now this time, instead of going between 0 and 2, we're going to find the integral between minus 2 and 2. So that's coming down here and down here as well. So now we're finding this area here. Now you can probably already see that one is just exactly the same as the other. So we could take our value that we've seen before and double it. But let's just confirm that that makes sense. So what we had before in our last example, where we went between 0 and 2, was 8. So this time, if we're right, this should come out to give 16. So integrating that, we'd get x cubed 2 to minus 2. So we get 2 cubed minus 2 cubed, which gives us gives us 8 minus 8, which would give us 16. So this will always work, this rule, for even functions. Write it a little bit more formally. For even functions, if we're finding the integral between minus a to a of a function, then that's the same thing as finding the integral from 0 to a and doubling it, so timesing it by 2. So let's have a look now at an odd function. So one of the most common odd functions is just x cubed. So in this one, we're asked to find the integral from minus 2 to 2 of x cubed. So we're finding this area and this area here. Now we know that when we've got something underneath the axis, that's like taking that area away. And we can see that these two areas are the same size. So if we have this area minus this area, then we should end up with 0. They're just going to cancel each other out. But again, let's go through and double check that that works. So integrating that, we'd have x to the power of 4 over 4 between 2 and minus 2. Substituting in, we'd have 2 to the power of 4 over 4 minus 2 to the power of 4 over 4. So that's going to give us 16 over 4, which is just 4, minus. Now minus 2 to the power of 4 will give us a positive 16 as well, over 4, and we'll just end up with 0. Again, more formally, for an odd function, if we're integrating from minus a to a of that function, we will just end up with 0. There's a few other important things to know about when we're evaluating definite integrals. So the first one is if we have an interval of 0 width, remember we're finding the area. So if we're finding the area of something that's not wide at all, it doesn't have a width, then that would give us an integral of 0. So that's if the bounds, the upper bound and the lower bound, are the same. Our next one is when we reverse the interval. So if we've got an interval from a to b, that's the same if we switch those bounds around. So from b to a, then it's going to be the same value, but it'll be negative now instead. The next one is an integral of a sum. So if we're trying to find the integral of two functions added together, then that's the same thing as finding the integral of each of those functions separately and then adding the solutions together. And the last one is looking at the integral of a multiple. So if we've got the integral from a to b of k f of x, where k is just a constant, then that's the same thing as pulling that constant out of the front and then evaluating the integral and multiplying it afterwards instead. So if there's a constant term, a constant multiplier, you can pull it out the front. All right, so that's having a closer look at definite integrals.